Okay, now, so here's what we got today. We're going to finish up, got to review position time, velocity time graphs, and then we got a lab, and life will be grand, so there you go. All right, so let's start from the beginning. You have a position time graph, and let's just say that we draw something like this, okay, and then it comes down, something like this, right? So here's positive numbers, and here's negative numbers, and here's 0, okay? So, Mr. Baker, tell me one thing that you can figure out based upon this position time graph. Tell me one thing that you know.
Well, it's like they kind of accelerate and then they stay in the same position and then they start to go backwards.
Okay, you're right, but let me tweak some things. Okay, let me tweak some things. So let's start at the beginning. How do you know that the object is moving?
Because the position is changing with the time.
Lovely. So from here to here, the position is changing. From here to here, the position is changing. Okay? So anytime you have a sloping line on a position time graph, this is subtle, but it's important. Anytime you have a sloping line on a position time graph, that means your position is changing. It's a key thing. Now, anytime your position is changing, the rate at which your position changes, you only have one of two options. Okay, this is it. You only have one of two options. Either your position is changing at the same rate all the time. In other words, you're going at a constant velocity. 5 meters per second, 10 meters per second, negative 20 meters per second, whatever that is. Or you're accelerating, meaning the rate at which your velocity, or the rate at which your position is changing. So, like, when you drove to school this morning, you started at rest. And your car was already moving when you got into it this morning, which would be kind of cool, but who's driving it? So, assuming that your car is at rest, you started to move. So your speedometer was showing 0, and then it went to 10, 20, 30, okay? And then maybe you cruised at 30 miles per hour in your parking lot, going through the street, okay? And then you slowed down for the stop sign, hopefully, okay? And then you sped up. So when you look at a rate of change in position, either your position is changing at the same rate all the time, or you're moving at a faster and faster rate of change in position, or you're moving at a slower and slower rate of position. Which means, basically, when you have a line like this on a position time graph, there's only one of two options. It's either showing constant velocity, and this is what the point of this lab is going to be today, or you have accelerated motion. Okay? Those are the only two games in town. You can't, well, I'm kind of accelerating. No, you're kind of not. You can't kind of accelerate. Now, how do you show constant velocity on a position time graph? Sydney? No. Close, but not this. Put a little angle to it. Angle. Or could be going like this, could be going like that. Lovely. So from here to here, notice that this is pretty much a straight sloping line, which indicates from here to here, this is a constant velocity because it's moving the same displacement in each time interval. Now, at this little segment, okay, so let's kind of focus on this little bit right here. Now, on this little bit up here, notice that there's a curve to it. Okay? So if there's a curve to it, that means that you're speeding up or you're slowing down. Okay, that's it. So if it's accelerated motion, that means there's some type of curve to it. Okay? There's any number of ways that that curve can be expressed. So basically, when you look at a line on a position time graph, you only have one of two options. It's either curving, indicating that you're accelerating, or it's straight, indicating that you're moving at a constant velocity. Now, Sydney, what does when it's actually like this, okay, what does that mean? Yeah, this means that I have a constant velocity, but it is 0 meters per second. So if you have a horizontal line, that means that you're moving with a constant that your constant velocity is 0. Okay, your position is changing. So if you go back to what Mr. Baker said, he says, well, it accelerated. Well, technically, this thing actually started moving with a constant velocity. Then it accelerated a little bit because then it had to slow down, because you have to slow down to come to a stop, okay? You know, I don't know how you could come to a stop at a stop sign without slowing down, okay? Kind of weird. So that means you're going to have to accelerate. Then you're at a constant velocity. Now, after this point right here, did it change direction? Courtney, did it change direction at this point right there?
Yes.
How you did? How do you know?
Because it's going to the negative. It's changing.
Okay. Can I give you a hint? What's the? Just pretend that you're in a math class. What is the sign of this slope from here to here? Positive or negative? Positive. Which means that I have a positive velocity. After this point, I have
A negative slope.
a negative slope, which means that I have now a negative velocity. Now, golden rule number 1. What's golden rule number 1, Riley? When something changes direction, it has to...
Velocity changes sign.
Perfect. So when you're going from positive to negative, you have to change direction. Okay? Now, here's another way that you can tell if something changes direction. If you're a math nerd and you study relative maximums and relative minimums, every time you have a relative maximum or a relative minimum, in other words, which is a fancy word for like, you know, the top of a mountain or the bottom of a valley on a position time graph, that means that you're going to change direction. Okay? So anytime something breaks over, going up or going down, that means that you're going to change direction. Okay? Now, Elijah, I'm moving at a constant velocity. Am I going towards the reference point or away from the reference point? From here to here. Beautiful. Why?
Come back to 0.
Yeah, I'm approaching 0, which is most likely the reference point. Now, at this point, Elijah, after this point right here, what happened? What did I physically do?
You're staying in the same direction.
I'm staying in the same direction because I have the same slope, and this just means that I went
Faster.
beautiful. Okay? So, like, here's the reference point, okay, this little green cart, right? So, in other words, I started over here, and I'm walking, and I just went past the reference point. Okay? Now, even though I went past the reference point, why didn't my velocity change sign? Hey,
Your velocity didn't change sign because you're still keeping the same direction that you were
yeah,
before.
exactly. I'm going in the same direction. I just happen to walk past the reference point. Okay? That's all. Nothing different. Now, did I change direction at this point? Mr. Abbott,
Yes.
how do you know?
It goes to positive.
Yeah, I go from a negative to a positive. Did I accelerate at this point?
Oh, yes.
Yeah, because you cannot maintain a constant velocity and change direction. Okay? It would be like you're driving, right, and you realize that you forgot your Mutant Ninja Turtle lunchbox at home. Okay, and this is bad. Okay, so you realize, man, I got to go back and get it. There is no way you can, in one dimension, go back to your house, get your lunchbox, and still maintain 20 miles per hour on your speedometer. Okay, it is not physically not going to happen. Now, let's talk about what happens when something changes direction. So I want you to visualize this. So I want you to visualize this. You're driving in your car, right? Okay, and you realize you've forgotten your Ninja Turtle lunchbox at home. And you're going in this direction. The house is back here. Okay? So you realize you're driving along, oh, forgot my Ninja lunchbox. So what's the first thing you're going to do? First thing that has to, realize you're changing, right? So you're go back and get it. So the first thing you're gonna do is you're gonna hit the brakes, right? So you're gonna hit the brakes, okay? You're gonna come to a stop. So the first thing that has to happen is that you have to slow down, right? Now, you're gonna slow down, and then what are you gonna do? You're gonna back up, right? True? So you hit the brakes, you're gonna back up. Okay, let's say you didn't go very far. You can just back up to the house. Okay, I'm not saying you're like 5 miles away. All right, you just pulled out of the driveway. Yeah, you're not going to back up 5 miles going down Mace Road. Okay, you're still in your neighborhood. You're going to back up. Now, so here's the question. So you slowed down, and then you sped back up. In between slowing down and speeding back up, what did you have to do?
Change direction.
I know that. But in between, what did you have to do?
Slow down.
In between slowing down and speeding back up, what did you have to do? Stop! Bingo! Now, listen to me. If you're going to change direction, there's 3 things that have to happen. Count them 3. The first thing is, you have to slow down. Down. The second thing is, you have to stop. And the third thing is, you have to speed back up. Okay? And it has to go in that sequence. You can't reverse this. You can't stop and then slow down and then try and speed up. Okay? And don't speed up, then try and stop, and then, no, it won't work. This is the only way that something can change direction. Now, let's look and see if that's what happens like right here, right? We figured out that this thing stopped, right? So it was moving with a constant velocity. Now, at this point, remember, what does the slope of a position time graph give you? Velocity. So as this reaches this point, notice that that slope becomes more shallow. It becomes more shallow because you are slowing down. Now, at the very bottom of this, and we'll talk about this later, something known as instantaneous velocity. Okay? If you draw what we call a tangent line, which I'm guessing you all at some point in your geometric use have drawn tangent lines to circles. Okay? Tangent lines on position time graphs gives you what's known as instantaneous velocity. We'll talk more about that later. So this, at that very instant, that's when you stopped. When this curve is at the very bottom. Now, then that line starts to get more steep, which indicates that it is accelerating and you're speeding up. Okay? So here you're slowing down, here you're stopped, here you're speeding back up. Got it? Good. Fantastic. All right? And it has to go in this sequence. Now, listen to me. Listen to me. Anytime something changes direction, without fail, even if I take, this green cart and I throw it up in the air, did it change direction? Yes? So, Mr. Cloud, how does that if I throw this up in the air, how does that represent these 3 steps? What happens?
Well, as it goes up, it slows down.
Yep.
Because if gravity's pulling it back down.
Yep.
And then it eventually stops.
Yep.
And then as gravity pulls it down again, it speeds up.
Beautiful. Okay? On the way up, it goes to a stop, and then slows down, and then starts speeding back up. So you throw something up in the air, this is the manifestation of these 3 things. Slows down, stops, speeds back up. Beautiful. Got it? Great. Now, let's talk velocity time graphs. When we started on these on Monday, or last Friday, today. So you got a velocity time graph. This is in meters per second, and this is time is in seconds. Okay, and let's start with something simple. Let's start with a horribly drawn horizontal line. A little bit. Okay, and let's say that this is 6 meters per second, and let's say this is 5 seconds. Okay, so let's start at the beginning. Mr. Moon, what does the slope of a velocity time graph give me?
Acceleration.
Slope gives acceleration. Beautiful. So rule number one, the slope is going to give you my acceleration. Mr. Moon, what is the slope of a horizontal line?
Like when
Huh? What is the value of the slope of any horizontal line?
it's 0.
0. So if I have a horizontal line on a velocity time graph, that indicates that my acceleration is 0, not accelerating. Now, just like on a position time graph, this graph has only one of two options, and one of two options only. Okay, this is it. Either you have a horizontal line and you're moving at a constant velocity with no acceleration, or it's moving up and you're speeding up, okay, because you're going away. Remember, this is 0 meters per second. So if you want to figure out on a velocity time graph if you're speeding up or slowing down, look at this. If the line is going away from 0 meters per second, you're speeding up. If the line is approaching 0 meters per second, you're slowing down. And if it's horizontal and parallel with the 0 meter per second line, guess what? You're moving at a constant velocity. So this graph only has one of two options. You're either accelerating and going away from 0 or towards 0, or you're at a horizontal line and you're not accelerating. Those are the only two games in town. That's it. And if you take these very complex graphs and you ask yourself, this isn't that complicated because only one of two things can happen. I'm either accelerating or I'm moving at a constant velocity. Okay, that's it. Do not make this difficult. Now, let's go back to this horizontal line. And you're at 6 meters per second by 5 seconds. Now, I want you to pretend that that's gone. Okay? Now, I have to undo about 12 years worth of geometric knowledge that you all have had imparted on you. Okay? And you're going, whoa, trust me, it'll be okay. Now, up to this point in your lives, you're given a rectangle that's 6 by 5. Miss Swanson, what's the area of that?
30.
30. Now, up to this point, what do you need to put on the end as far as units goes?
Flat.
Huh?
Just flat.
Oh, no. Let's say these were meters and meters. What would you say the area was?
Meter squared.
Meters squared, right? So up to this point in your lives, from the past 12 years, every area that you have ever found has ended up in something squared. Meters squared, inches squared, yards squared, miles squared, something. Up to this point, every math teacher in the world has taught you that area is measured in something squared, right? True? Okay? And that's been drilled into your heads, and that's been true. Now, keep that in mind. I want to make this go away. Pretend that you don't know anything else. Whoa. Okay, we're good. Now, I'm going to tell you that something is going to run for 6 meters per second for 5 seconds. Okay? Right? 6 meters per second for 5 seconds. Daniel, how far would you run if you ran 6 meters per second for 5 seconds?
You'd run 30
Huh?
meters.
30 meters. You take 6 meters per second times 5, the seconds cancel out, you would get 30 meters. True?
Yeah.
Okay? Distance, right? How far you went? 30 meters. Cool. Now, we're going to go back to this. I have a rectangle, and this is what's going to flip you all out, but don't let it. It's okay. I have a rectangle that is 6 meters per second tall. And you're going, whoa, you can't have that. That's the velocity. You can't measure height in meters per second. Oh, it's going to get weirder. I have a rectangle that has a base of 5 seconds. And you're going, whoa, no, say it isn't so. You can't measure a length in time. Sure I can. 5 seconds. I've got a height of 6 meters per second. And you're going, that's not right. Yes, it is. It's completely arbitrary how I set my scale. This thing is 6 meters per second tall. This is 5 seconds. Okay? Now, here I have a rectangle that's 6 meters per second tall by 5 seconds. Paige, what's the area of this rectangle?
30 meters second squared.
Close. You took 6 meters per second, right? Times 5 seconds. Now, when Daniel took 6 meters per second times 5 seconds, he got 30 meters.
30 meters a second.
30 meters?
Yes.
Are we good? 30 meters?
Yeah.
You sure?
Yes.
You should be. Okay. Now, so, I'm really not trying to be that tricky. So, this area right here, between the line and 0 meters per second, oddly enough gives you displacement. So, on a velocity time graph, area equals displacement. Now, the reason that I say displacement and not distance is because if this had been negative 6 meters per second for 5 seconds, the area would have been negative 30 meters. So you can have areas up here, you can have areas down below the 0 meters per second. Doesn't make any difference. That's why we say that it's displacement and not distance. So area represents displacement. So where are we at on the golden rules? What are we up to? Number 3? Okay, so golden rule number 4 is that on a velocity, so here's golden rule number 4. On a velocity time graph, area equals displacement. And it's between the line and the 0 meters per second. And it doesn't make any difference what the shape is. It could look like a triangle, a squirrel, an orca. It doesn't make any difference. Okay? It's easier if it works out to be a rectangle because then it's just this, one dimension. Now, if you ever study calculus and you find the area underneath a line by taking the integral, that on a velocity time graph, that's what you're finding. Okay, so if you do calculus and you take the integral, that's what you're finding is the area underneath that curve, which is going to represent displacement. Got it? Good. Fantastic. All right. So, there's one last golden rule that we need to come up with, and then we're done. So, let's talk velocity time graphs. Okay? So let's say that you have a line that's going at 6 meters per second for 5 seconds, and then it drops down. David, what is this object doing? If I gave you this velocity time graph and say, what can you conclude this thing is doing? What would you say?
It's slowing down.
The entire time?
It stays on a constant velocity and then it starts slowing down.
How do you know? You're right, but how do you know?
The slope's going down.
And it's approaching 0 meters per second, right?
Yes.
Okay? So, perfect explanation. So, this thing is moving with a constant velocity, and we said if we found this area, that's how far you're going to go. Okay? So, you're moving at a constant velocity. And then David says it begins to slow down, and we know that because it's approaching 0 meters per second. Lovely. Okay? Now, pretend that you all are in math class. What's the sign? I just want the sign. The sign of the slope of the line coming down like this. Elijah. Negative. So, now, since the slope on a velocity time graph represents acceleration, this means that I have negative acceleration with positive velocity. Right? Now, David just said if I have that I'm slowing down. Okay? Because I'm approaching 0 meters per second. So, anytime, here's golden rule number 5. Golden rule number 5. If velocity and acceleration have opposite signs, you slow down. So, number 5 is this. If velocity and acceleration have opposite signs, that means that you slow down. Okay? There is no exceptions to this whatsoever. Now, the converse of that would be what? Danny, what would the converse of this be? That if they have opposite signs, you slow down, so if they have the same signs, you speed up. Beautiful. So the other side of that is if they have the same sign. Oh, that was horrible. If they have the same sign, guess what? You speed up. Okay? Again, there's no exceptions to this whatsoever. Now, notice, pay attention to what I did not say. Notice that I did not say, oh, positive acceleration always means that you speed up, and negative acceleration always means that you slow down. Okay? Not true. The only thing that's true is if you're slowing down, they have opposite signs. You might have positive velocity with negative acceleration. You might have negative velocity with positive acceleration. If they have the same sign, you speed up. Could be negative and negative, could be positive and positive. So let's look at this. Okay? So right now, we started with this negative acceleration, positive velocity. We're slowing down. Now, if you're not sure, okay, here's another way that you can view this, and this is something that David hit on. If this line is approaching 0 meters per second, that means that you're slowing down. So a lot of times what we'll do on our graphs, we'll put little down arrows, and this is what you're going to do on the lab today. You're going to put a little down arrow that indicates that this thing is just slowing down. So if your velocity time graph is approaching 0, that means that you're slowing down. Now, what if the graph did, let me kind of clear this and start over. Velocity time okay, so let's talk this. Here to here, what's it doing? Am I moving? Yes. Why, Riley? You seem hesitant.
You are moving
How do you know I'm moving?
because it's not like one point, it's a line.
Well, so is this line.
Right.
Right. Here's the line of 0 meters per second, right?
You're going along with it, so you're just staying at the same velocity over time.
That's not 0, right?
Yes,
Okay, so this is a non-zero value.
correct.
Okay, so this is like maybe positive 6, right?
Yes.
So I'm moving at a constant velocity, it's not changing. Riley, from here to here, am I slowing down or speeding up?
Slowing down.
How do you know?
You're getting closer to 0 meters per second.
Also, what's the sign of this slope, positive or negative?
Negative.
So here I have negative acceleration with positive velocity. That means that I'm going to slow down. Now, for this little segment right here, what am I doing? Elijah, right here. This little bit right there where it's horizontal.
Down and then stop. Oh, stay.
I'm still moving, but with a, okay, right? So here I'm at constant velocity again. Now, from here to here, Paige, what am I doing? Speeding up or slowing down?
Speeding up,
How do you know?
because it has a positive slope, because the acceleration is positive,
And my,
velocity is negative. No, same, it's positive.
so you're going to
Same
speed
side,
up.
speeding up, yes.
So here I'm speeding up. Constant velocity again. Now, from here to here, what am I doing between these 2 points, speeding up or slowing down? Mr. Abbott.
You are staying the same.
Oh, dear Lord, no. From here to here,
You're slowing down.
how do you know?
Because you're approaching 0 meters per second.
Yes, I'm slowing down. I have negative acceleration with positive velocity. Now, here's the big kicker. Okay, here's the big kicker. I want you to focus. What 3 things have to happen to change direction?
Slow down.
Slow down.
Speed up.
Speed up.
See, I'm on top of it. Right now, I am.
Yeah, right now you are. So, Am I slowing down?
Yes.
Am I going to stop?
No.
Really?
Yes.
Correct me if I'm wrong, but if I have a velocity of 0 meters per second, that's pretty much stopped.
And then you speed up.
How do you know that I speed up?
Because you have the same slope, the same sign.
Of?
Velocity's negative and time's negative. Or whatever.
Close.
Acceleration's negative.
Ah! So now I have negative acceleration with negative velocity, and now I begin to speed up. So look, how do you know that I change direction? What's golden rule number one? If you're going to change direction, one has to change sign.
Velocity.
Velocity. Does velocity change sign when I cross this point?
Yes.
Yes. Now, look at why this makes sense. Why the three things have to happen for you to change direction. Look at this line as it's approaching 0. If it's approaching 0, you have to be doing what? Slowing down. You have to hit 0 meters per second, right? And then the velocity has to change sign, and then you have to go away from 0 meters per second, which means you're going to do what? Speed up. I promise you, there is no way that you can change direction by making this line go away from 0 meters per second. Okay? That will not work. Okay? Because you're just going to keep going faster and faster and faster. The same thing is true down here. If you cross this line, that just means you're going further and further and further and further away from 0, which means you're going to be going faster and faster and faster. Okay? So, visualize this. Now, if you were to actually draw this, okay, now I want you to visualize what's going to happen. So you would be moving along at a constant velocity, and then you would do what? Would you change direction? No. Why?
Because you haven't passed the x-axis.
That's right. The only thing I've done is slow down. So imagine that you're driving, okay? You're driving through, and then you're going to slow down, okay? And then you're going to maintain the constant velocity, and then you're going to do what?
Speed up.
Speed up, maintain a constant velocity, then you're going to slow down, and at this point you realize, oh, I forgot my Ninja Turtles, right? So at this point you slow down, stop, and then you
Speed up.
speed up in the opposite direction.
You got it.
Got it?
Yeah.
Beautiful. Okay, now stop that for a second because I got to get... Okay, so what you're going to need for this lab is a couple of things. You're going to need this is what we call a spark timer, oddly enough because it makes little sparks, okay, and it keeps track of time. So hence the term spark timer. Now, I know. Oh, it gets better. Oh my God. Now, this is what we call a CVD, which is a technical term for a constant velocity device. Now, they call it a constant velocity device because they can charge us like $40 for this. If they just called it a bulldozer, they can only charge 10. But because it's a constant velocity device, they can charge a lot more money. Now, let me explain what this thing is. There's a little on-off switch, okay? And if you turn it on, okay, it moves at a relatively constant velocity. And there's going to be like 5 of them in the back. Let me explain what these aren't, okay? I don't want races between them. I don't want you to tie a string between them to see which one can outpull the other one, okay? I know you would, okay? I don't want you to set up a little demolition course to see if it can like climb up and over your notebook. It can, okay? It's 4-wheel drive, right? So I already know the capacity of these things, okay? And I don't want you to push it down and go, boom, room, room, okay? Bad, okay? Bad, bad, okay? Their sole purpose is to generate a constant velocity. Now, this is going to be the most technical part of the lab. You need to take this tape, okay? And you need about yay much, okay? Not yay and a skosh, okay? Just about yay much.
Yay and a skosh.
Yeah, just yay, not yay and a skosh, okay? Maybe you can get by with yay and a titch, which is just a little bit, but generally you just want about yay much. Now, it's true, it's technical measurement. Right, now, this tape has 2 sides to it. It has the metal coating side and it has the plain paper. The metal coating side has to go up because what it's going to do is conduct electricity, and then you're going to get, this is going to make little marks on it. Now, when you look at this, this thing has two switches, an on-off switch. Hopefully nobody struggles with that one. And then you have a 10 hertz and you have a 60 hertz, okay, which is HZ. Anybody know what hertz measures? And it's not pain. This is HERTZ.
Go for it.
No.
Frequency.
Frequency, okay, which is vibrations per second. So you want this thing set at 10 hertz, which means that you're going to make 10 marks per second. If you set it over at 60, it's making 60 marks per second, which means it's just going to basically turn into like a blob of marks, okay? So make sure that you're on the 10 hertz setting. So you're going to set this down, and it's got a little arrow that indicates which direction this thing needs to go. So there's a little bit of advanced work that you need to do. You're going to take the tape, and you're going to attach it to this. First off, you want to make sure that you know which direction this thing is going to go, because it's going to pull the tape through the timer. So you want to make sure that you know it's going to go away from the timer. Don't hook it up and have it climb back over the timer. Poor form. Okay? So make sure that you know which direction that it's going to go. Also, don't set it up right at the edge. We're not going to study accelerated motion caused by gravity. We'll deal with that later. Make sure that you have enough room to pull this through. Now, here's the most important step that you do. You want to take the tape, and don't screw this up, and force it through, and then tape it to the machine. And I have to say this, because don't tape it to the machine first and then go, it won't fit. Had that happen. This is why I always say this. So make sure that you put it through the timer, okay, through the timer, and then take a little piece of tape and secure that to the constant velocity device. Okay, so you can have some action like this. Now, this sequence is actually true. Okay, this is I'm serious on this one. What you want to do is that you want to listen to this sequence. You want to turn the tape timer on, okay, then turn on the machine, because we want this thing starting from rest and then speeding up. Okay, so you're going to turn on the tape timer. Then once you get that up and running, then turn on the machine, okay, and have room so it climbs all the way across and doesn't go up the notebook. So what's going to happen is that, and I'll draw this bigger, but what you'll see is that it's making a series of dots on the tape. Now, as it speeds up, what do you think is happening to the distance between the dots?
Closer together. Further apart.
Further apart, because it's speeding up. This thing is vibrating at a constant 10 dots per second. Okay, it's making 10 dots per second. So that's a fixed value. So as it speeds up, it's going to pull more and more tape through during each interval. Now, theoretically, once it reaches a constant velocity, what should happen to the distance between them?
Same.
Should stay the same. Okay? So you're going to see the dots getting further and further and further apart, and then hopefully it flattens out and you get like the same distance in each interval, or pretty close to it. Okay? Good? All right. So what you're going to do is that you just generate one tape per group. Okay? Everybody's going to use the same data. So you're going to have a tape, okay? And what you're going to see is a couple of dots at the beginning. This is when you just turned it on before it started to move. And then you're going to see a set of dots, and then you're going to see another set of dots, another set of dots, another set of dots. So this first distinguishable interval is interval number 1. Okay, so that's the distance between where you started and that first dot. So on that data table, okay, and it's actually misspelled, it says intervals, it should say intervals. So this is going to be interval number 1, and then this distance between those is number 2, here's number 3, here's number 4, okay, so on, right? And you just have to generate 10 intervals, okay, that's it, just 10 intervals. Now, because we're going to be dealing with such small distances, go ahead and measure, just put this thing in centimeters. But be consistent with your precision. Most of these measuring devices you can estimate out to at least like 1/10 of a centimeter, if not the 100th of a centimeter. So be consistent on how you're going to measure this thing. So what you're going to do is that if you look on that data table, you have 3 columns. One that says interval, so you got 1, 2, 3, 4, okay? And then the next one says, what's the next column over? Average velocity? Displacement. And then it says velocity and then total displacement? Okay. Okay. So your displacement is how far it moved in that first interval. So what you're going to do is you're going to take a meter stick or a ruler and you're going to measure the distance between that first dot where you started and the next set of dots. So let's say that, I'm just going to make up a number, let's say that was 1.10 centimeters. Now, to make this easy without going through some weird math, we're going to let the velocity be whatever the displacement is in that interval. Now, realistically it wasn't because it was actually speeding up a little bit, okay? But over that short of time span, it was only like 1/10 of a second, we're going to let the velocity be the same as the displacement. So whatever numbers you have here in your displacement is going to be the exact same numbers that you're going to put here in your velocity column. Okay? They're going to be the exact same. Now, your total displacement is how far you have moved from the beginning. So at the end of the first interval, how far have you moved? 1.10 centimeters. Okay? Don't make that difficult. So your first column is going to be the same, or your first row is going to be the same all the way across. You travel 1.1 centimeters, we're going to say that's the velocity, that's the total distance that you went. Now, in the second one, let's say you measure that. You get 2.30 centimeters because we sped up a little bit. Okay, so we traveled a little bit further. So that's also going to be 2.3 centimeters per interval. Now, this total is going to be how far you have moved from the beginning. So we went 1.1 and then we went 2.3. So what's the total distance that we traveled? Yeah, this is going to be a running total of this column. So this is going to be 3.40 centimeters because that's how far we've moved from where we started. Then, let's say this is, I don't know, 3 centimeters. That would be 3 centimeters, and this would be like 6.4. So, you're going to measure the distance between the individual sets of dots. That's going to be the same as your velocity. You're going to keep a running total to get here. Typically, you end up something around 20 to 30 centimeters. Typically, that's where you end up. Okay? Now, dot that. Now, here's what I want. The first thing you're going to do is you're going to draw, on that section down below, you're going to draw a velocity time graph. Okay? Now, at time 0, what was your velocity? 0. Okay? Now, even though I've been preaching the meters per second and all this good stuff, just draw this in centimeters per interval. Okay? So set your y-axis to be in centimeters per interval. Make your x-axis intervals. Okay? So you're going to have intervals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You're going to have a sheet of graph paper. So help me. Do not draw this graph in one little corner. You spread this graph out because there is a whole bunch of things you need to do on this graph. Do not draw this as a tiny little graph. Now, one of the things it's going to ask you to do is indicate when it's speeding up or slowing down. The easiest thing to do is what we talked about before. If on your velocity time graph, basically, if your line is going away from 0, draw an up arrow. If it's going down towards 0, draw a down arrow. If it's horizontal, you don't have to draw anything. That's it. Now, one of the things they also want you to do is to calculate the average velocity. If you remember from Friday, I know, which is a stretch, remember your average velocity is your total displacement divided by the total amount of time. You're going to know what the total displacement is at the end of 10 intervals because you're going to have this number. Okay? You're going to know what this is. You're going to know what the total displacement is at the end of 10 intervals. So to get your average velocity, take your total distance traveled at the end of 10 intervals, divide that by 10, that's your average velocity. You're just going to draw that as a horizontal line on your velocity time graph, saying on average, this is how fast we went. Then you're going to draw a position time graph. To get your position time graph, you're going to plot total displacement versus time. So basically what you're going to show is how far this thing is moved as a function of time. So the first graph of velocity time, you're going to do this column versus time. The second graph that you're going to draw is total displacement versus time. Okay? They're going to look completely different. Now, here's the whole point. If you look at the questions that I want you to answer, where's my glasses? What did I do? So, when you get here on this backside on question number 4, where it says, write an explanation for what the position time graph shows, point out any changes in the slope of the line, describe what the slope represents. Okay? You're going to have a graph. You're going to say, basically, it's a narrative. Hey, here's this position time graph. This is what it looks like. This is what it means to me. All right? Okay? Does it mean that I'm speeding up? Does it mean that I'm slowing down? Did I change direction? Am I moving with a constant velocity? How do you know? Now, the single most important question on this lab is question number 5. Okay? When I type up this question, here's the point. I want you to reference, listen to me, the shape of both graphs in indicating the type of velocity that is going on. So if, let's say for example, you look at your velocity time graph and you go, well, I've got this big spike, okay, going away from 0 meters per second. You got this big spike on this velocity time graph. What does that mean? How do you know that it's speeding up? Is it slowing down? Is it moving at a constant velocity? Then, if you have that big spike on your velocity time graph, how does that show up on your position time graph? Is it a straight line? Is it a curved line? Is it curving up? Is it curving down? Now, listen to me, and you will hear me say this again and again and again. Both graphs, your position time graph and your velocity time graph, listen to me, have to show the same thing happening at the exact same time. So if your velocity time graph indicates that you're accelerating and you're speeding up, your position time graph better show that. If your velocity time graph shows that you're moving at a constant velocity, how does that show up on your position time graph? So in other words, you can't have your velocity time graph showing that you're moving at a constant velocity, and at the same time your position time graph indicate that you're speeding up. They have to show the same thing at the same time. Okay? All right. I'm done. You're on your own.